Alrighty, so here is a pure liquid with its vapor above it. Okay, the pressure in a sealed container, right? The pressure up above that liquid when it's at equilibrium, we call that the vapor pressure, right? When it's at equilibrium, okay? This is for pure liquid and gas above it, okay? Let's mix a certain amount of solute in there, and it has to be a non-volatile solute. What does non-volatile mean? Absolutely. 0. Does not vaporize. Okay, so a molecular, meaning it's just molecules, they don't break apart or anything. Non-volatile means it has no vapor pressure of its own, okay? Solute. Okay? So something like sugar. Sugar is molecular, right? It's made of only nonmetals and just individual units, sugar molecules. It has no measurable vapor pressure. Most solids at room temperature have no measurable vapor pressure. So this is dissolving sugar in water. Okay? Why do you suppose we mix that sugar in? Why do you suppose the rate of vaporization is reduced by the solute? Right? This upward arrow is now shorter than it was before. Anybody have any ideas why that is? It's actually simpler than you would think. Think about where vaporization has to happen.
The solute, when it's going in, is causing the surface area of the water to decrease, so there's not as much room for gas to escape.
How would be that?
Taking up some of the places that the water molecules would be otherwise.
I think that's a perfectly fine way of thinking of it, right? If vaporization can only happen on the surface, assuming at some point in time you would have these solute molecules on the surface, right? I mean, they're evenly distributed throughout, but as soon as one of them is on the surface, that's blocking a place where one of the liquids could be vaporizing from. Okay? That's one way of thinking of it. Another way of thinking of it is increasing intermolecular attractions, okay, between those solutes and the solvent particles around it. Usually when a solute dissolves, it has a shell of solvent molecules all the way around it that actually ends up being more attracted to that than it is to the others. Okay? But both of those work perfectly well in remembering what's happening here. Okay? So rate of vaporization is reduced, okay? But rate of condensation, okay, has not changed. Okay? We didn't change anything with the gas up there, but if we're putting fewer molecules up into the headspace, that means when equilibrium is reestablished, there will be lower pressure, right? This is going to be the reduced vapor pressure. Okay. So I'm going to give you some symbols here. Vapor pressure, we're going to call that P with like a superscript 0 after it. We're going to use that symbol an awful lot. You can sort of think of it like original. Okay? The vapor pressure of the pure solvent, that would be like the original pressure. And then this reduced vapor pressure, that would be P solution. Okay? Sometimes we could call this P0 solvent. Okay? But here's the key. Adding a solute prevents some vaporization. So So the vapor pressure of the solution is less. Okay? We've reduced the vapor pressure because of what we've added in there. Here is Raoult's law. Raoult's law. We had Henry's law. This is Raoult's law. Actually, not too different. The vapor pressure above a solution is equal to the mole fraction of that solvent times the pressure, the original pressure of the solvent, right? Mole fraction of the solvent, and that's important, right? So that would be moles of solvent divided by total moles. Okay. Now, let's think of this going to an extreme. If it was just pure over there, what would the mole fraction of the solvent be? It would be no. Think of moles of the solvent divided by total moles. It would be 1, right? Because you would have so many moles of solvent, but that would be the same as the total if it was just solvent. Okay? So with a pure substance, okay, the pressure mole fraction would be 1, which means it wouldn't be modifying the original pressure. Okay? Now, as soon as we start mixing something in, what happens to the mole fraction of the solvent? It goes down, right? If we mix a little bit of something in, the mole fraction now goes down to 0.99 or 0.98 or 0.95 or 0.8 or something like that. Okay? So by multiplying that mole fraction by the original vapor pressure of the solvent, then what happens to the vapor pressure of the solution? What do you think? Yeah, it decreases. Okay? It decreases literally by whatever fraction of solvent moles that you have right there. It's a very simple equation. Probably works best to literally think about the surface area on the top of that solution there. Whatever fraction, whatever mole fraction you have of solvent, that's what can do the vaporizing, right? If half of the molecules on the surface were solvent molecules, you'd only be able to vaporize half as much as you originally did, right? So it's really simple as long as you remember we're talking about mole fraction of the solvent there, okay? So let's calculate the vapor pressure, okay? So that's going to be P solution. That's the vapor pressure of the solution. When 0.137 moles of sucrose are added to 27.4 moles of water. So we're going to need a mole fraction there. And here's the original pressure, 92.5. If you want to write an equation, P solution, mole fraction of water, is P0 of just pure water, like that. So make a mole fraction in there. You could calculate the mole fraction separately if you want, multiply it in there, or you could have it as part of that equation. Okay? But if we're thinking of the proportion of molecules on that surface that are able to vaporize, that I think makes it a little easier. How would we calculate the fraction of molecules on the surface that are able to vaporize? We're given moles of sucrose and moles of water. It's the water that does the vaporizing, right? Did anybody divide out the mole fraction separate? What'd you get for that?
0.995.
Yep. So it's essentially 0.995. .995, yep, something like that, times the original vapor pressure, which is 92.0, right? Now, make sure that you have a good conceptual understanding of this. The pure water is 92.5 millimeters mercury. That's the pressure above just a sample of pure water at this particular conditions, whatever. We mixed a little sugar in there. We now have only 99.5% of those surface molecules are available to evaporate. Okay, 0.995. Still mostly water, right? We've just lowered that proportion of water molecules on the surface by just a little bit. Okay? So the vapor pressure is going to be lower, okay, but not much lower. Okay? A little bit lower. It's going to be exact proportion for the mole ratio of that actual solution itself. Okay? Does that make sense? Where do you suppose the big part is that's easy to screw up, though, in this one? Yep, absolutely. Here, let's write it out. Solvent. That is huge. It's because our starting point is like 100%. Right? Our starting point is a mole fraction of 1, okay, which would be just pure solvent. Mixing in a little bit of solute will bring that mole fraction down, like to 0.995 or 0.98 or 0.97 or something like that when we have small amounts of solute that are being added to it. Okay? Does that make sense? That's going to be very important. This is the in the case of vapor pressure lowering, the solvent is the volatile component, okay? Because we want to have that mole ratio, that mole fraction there be how much of it is able to vaporize at the surface. Okay? That makes sense? Good there. Okay. What if we have an ionic solution? Well, what's different about ionic solutions is they break apart when they dissolve, right? If something is ionic, its ions come apart, and each ion is individually dissolved. Okay? So let's say we have 1 mole of sodium carbonate. How many moles of dissolved ions are actually produced when 1 mole of sodium carbonate fully dissolves? What do you think? Maybe let's write out a little equation here. Let's say if we have sodium carbonate, and it's Na2CO3 because of the charges, right? But when that dissolves, like remember when we were writing net ionic equations, we broke up ionic compounds into their ions. How many sodium ions are there in this formula? There are 2 sodium ions that get dissolved, call that AQ, and there's 1 carbonate ion. Carbonate's 2 minus. Okay. So how many moles of dissolved ions are there in this 1 mole of sodium carbonate when it dissolves? 3 moles. Okay. I'll give you a little preview for next time. We're going to use lowercase I. For that, ideal moles of per mole of solid. We call that lowercase I. talk about that more next time. Okay. So when we're doing this vapor pressure, though, it's the mole fraction that's going to change as a result of this. Let's say I have 1 mole of sodium carbonate dissolved in 10 moles of water. For vapor pressure, we're interested in the mole fraction of water, which is going to be 10 moles of water and then on the bottom it's the total, right? But what should I add to that 10? Well, we would use 1 mole if sodium carbonate were molecular. Okay? If it was sucrose, if we were adding 1 mole of sucrose, sucrose is molecular and it doesn't break apart. But when we've got an ionic substance, it breaks into however many ions it has in its formula. So I should really be adding 3. Essentially 3 times 1.0 moles. Another way of thinking about 3 ions per formula unit. Okay. So it's 10 divided by 13. It's 0.769. Ionic solutes multiply I by moles solute. If we were to make a general formula for that, N solve N I times N solute, like that. Okay. So if we want to know the vapor pressure over this solution, P over that solution, it's going to be mole fraction of water times original pressure. It's going to be that 0.769 times 25. Be like 19. So you get a lot more bang for your buck with ionic solutes because they break themselves apart into however many ions are in their formula unit, and each of those ions has the same impact as one, say, molecule would. Okay? So that gives us a good start for next time when we're going to talk about colligative properties, changing properties based on concentrations.